So today we're very happy to have Lorenzo Ricci, comes from Maryland, and he's going to tell us about his upcoming work diploma on conformal colliders. So please
Thank you very much. Thank you for the introduction. Thank you for having me here. It's really a pleasure to be here and to talk about some work in progress that I'm doing in Maryland together with Ramon. So first of all, let me tell you what is the general idea, what we're doing, and why we're doing that. And let me give just a short introduction on the idea of conformal collider, more precisely energy correlator. The idea is very simple, and we're all very well educated on how to compute S matrices or amplitudes, starting from initial state to final state. And we know how to do it very well. I mean, we know that the amplitude program is doing tremendous progress, but at the same time, we know that when we go to observable, when we go to measure something, we actually never measure the amplitude, but we measure something else. We prepare our state, so we don't choose the final state. We let the state evolve. In a collider experiment, for instance, can be proton-proton or electron-electron in electron collider. And after the state evolve, at the end, we will gonna measure some of the property of the final state. With this notation that I will use later on, what I'm just denoting with the dashed line are all the possible final state. And on these states, we are going to act with some detector, which is in general just some operator. So in practice, what we are doing at the experimental level is really a quantum mechanics expectation value in a state.
But aren't the final states asymptotic states? So isn't that dashed line typically a curve?
Asymptotic states. They need to be asymptotic states, actually, yes.
So these are not local operators.
Something that, yeah, next slide, yeah. So from this perspective, the left-hand side seems a bit weird if you start from the right-hand side. In particular, you can see that to measure amplitudes, what we need to do is to select very exclusive final state. In principle, we need infinite number of detectors to be sure that we are selecting a precise final state. Now, we know that this works, we know how to do it, but sometimes, like in QCD, or in theories where this matrix is not even well defined, the right-hand side can be the correct approach. Now, the most simple detector is actually this energy detector. It's an local operator. So it's actually just defined as the stress tensor sent on the celestial sphere, so at infinite distance in a given direction n, integrated over time. And so the price to pay to have this detector is actually to define a local operator, but then we can define the expectation value of this local operator as the expectation value of our detector. So what we are going to measure. This idea was originally proposed long ago for a plus C minus 2D2 hadrons. And let me say that recently the understanding of this observable has undergone really tremendous progress on many fronts, from both the theory and the phenomenology.
And you keep T fixed when sending R to infinity?
You fix, sorry?
T fixed.
T is integrated. So you fix up to, you send R as large as you can, and then you integrate over T. Yeah, okay. Moving. Oh, it's moving.
It moved.
It moves. Yeah. Okay, so let me tell you, at least in my opinion, why the reason why this approach is convenient. The first of all is that the observable infrared safe. So at least from the technical side, when you start doing calculation, you don't find all these funky divergences that we usually find, and then we have to define some inclusive observable where they magically cancel. I mean, well, as it should be. This is the first reason. The second reason is that they scan different scale. So just to give you an idea, I reported just this plot from this paper, where what they did is just look at all the set of jets from the standard model from LAC, and as a function, I mean, and they basically measured energy correlation, so the correlation of two energy detectors as a function of their relative distance.
And this is infrared safe if you choose appropriately the initial states, because in the general proof for cancellation of infrared divergences, you also have to sum over initial soft photons.
Yeah, I mean, in this case, you have to, I mean, for instance, you have to choose, yeah, I mean, a state that is appropriate state, yes. In a plus C minus collider, that's fine, because you are accepting the QCD vacuum with an operator, which is just a pure photon, which is actually a single entanglement under color, so there is no problem, but yeah. Here you need to define initial state, which is properly defined, so to be true. And so if you do this exercise, what you find is that for large angle, you see basically a straight line, and you can see that because you basically measure the energy carried by quark and gluons before they start eventually showering and going into hadronization. And you can see that is a straight line, and is what is predicted by perturbability QCD. When you start going to smaller angle, at some point you see a transition, and this is because you are hitting the QCD scale. And when you go to even more angle, you just start seeing the effect of just free streaming hadrons. And this RL, for we're not familiar, is just an angular distance that you use in collider physics.
Why is it going down?
Why is it going down?
Yes.
I mean, at some point you start your theory, finite time, it will just be made of pions,
Yes.
say that they just propagate and they are free streaming pions. So this is just the power law that is given by free streaming pions.
Okay.
And the third reason is that since it's infrared safe, it can be precisely calculable in perturbation theory. And actually, earlier this year, last year, 2024, they released the first measurement of energy correlator inside jets, and they use it to do a proper extraction of alpha strong. So in the first plot, they said that for the large angle, basically you just predict a power law, and this power law you can measure it very well, and it's going to depend on alpha strong. And measuring this power law for jet of different energy, they managed to get, as of now, the best measurement of energy correlator inside jets, or alpha strong inside jets. So I guess this is a proof of principle that there is something that can be extracted from this kind of observable. Now, let me give you also the three theory reason why I believe it is promising. First of all, is that these objects are defined independently of the mathematics. So also in conformal field theory, for instance, and this was the whole idea of the conformal collider program. The second reason is that energy is conserved. So I know what I'm talking about. I don't have to, from the OV to the R. So energy is the same, whether I'm exciting the theory to very high energy or to very low energy. And differently from particle is always a well-defined concept in my theory. And finally, is that it's calculable in CFT with small expansion parameter, and as for instance in QCD, and this tells us that at least with some control, so in some regime, like for instance large N or large charge, we can do actual calculation and we can have some actual prediction. Now, myself, I come from phenomenology. I do mostly collider phenomenology. So let me tell you what is for me at least the holy grail of this program in this precise moment. And we have the LAC. The LAC is running and is providing really a tremendous amount of data. And at the same time, let me also say that there is a lot of effort in doing analytic calculation of these objects. So I guess right now we should try to use them to improve our understanding of the standard model, or at least test new physics beyond the standard model. And actually, there are already many applications. I just got in 3 of them, but there are really many for testing some property of the standard model.
But you know what happened to the bad guy in Indiana Jones in the Last Crusade when he not from the humble one.
And so coming from the BSM, I'm asking what are the options? I mean, what are the scenarios where we can actually use energy correlator and we can try to use them to learn something about new physics? And there are basically 2 options that I could figure out. The first one is they are used to study standard model jet, QCD jets. So in particular, if we have some new physics that goes to jets, eventually we can try to report the way we do jet substructure to use this observable and maybe to improve our understanding of standard model jets produced by new physics. This is quite canonical, but can be a possible approach. A second less canonical approach is to study for situations where we don't have much control of the theory. And one case is where we produce new physics that is itself strongly coupled, and itself try to produce final state with very high multiplicity. So a sort of BSM jets that we can imagine from a sector which is completely analogous to the standard model. So it's not too exotic, it's similar to what we have now. In principle, you would say, okay, but then how do you detect energy from the BSM? If the sector has gap, the BSM state in the R, they will eventually go back to the standard model and form, in some sense, a sort of with standard model jet that can actually look similar to standard model. This is already a program, not for energy correlator, but in general, to search for this kind of new physics model, and they are usually called in the valley. And yes, if the BSM eventually turns into a standard model, in principle, one can try to look inside standard model jets to look for energy patterns that are not the proper one that we expect in the standard model. Okay, and that's basically what I will try to argue that can be done. Before that, since we are not yet at the stage of phenomenology, I realized that it might be useful to give some very short warm-up, just talking about another work, I mean, some part of another work that I wrote some time ago, where we study actually canonical standard model jets looking for new physics. And this is just to give you an idea how these objects are used in real phenomenology. Okay. So what we look at, this simplifying a bit, is really the most simple object, hadronic object that you can imagine a collider. So an hadronic W or Z boson that go back exactly to QCD. And as a setup, what you can imagine to simplify is to have an A plus C minus collider that produce our object, so either W or Z boson, say W, plus something else that we say to be leptonically, so that there is no issue in defining a single state, which is our WZ that excite the QCD vacuum. And all the rest is calculable in perturbation theory is outside the QCD vacuum. So the total cross-section for this process can be simply written as two factors. The production, which is usually called art for our vector boson. This is completely perturbative under this assumption, so we can just compute it in perturbation theory as we know how to do it, times some decay. The decay in general, the true decay is really complicated because it will be sensitive to hadronization, it will be sensitive to all the QCD dynamics that arise from our W or Z decaying. And so in particular, this object is in principle differential cross-section for our WZ to hadrons. Now, the ideal energy correlator is that you don't need to study all of that, which is complicated in simulation, but you actually can define a simpler object where you just insert some energy detector in this decay matrix. I will define it slightly better in a second. So the idea is that you just act on your hadrons with some detector, which is counting the energy. So you ask a very more inclusive question, very more simple question, and you try to extract some information from this question where you actually have some control. So you can actually do some perturbative calculation. And the question that we ask is, can we use an energy correlator to describe this state and its evolution in QCD? So let me try to be slightly more precise on how this is formalized. So again, we're just focusing on the decay matrix. The production is perturbative and don't tend to say anything. This expectation value is written as a Westman function in of this detector. So these two operators are going to excite and produce our state, and we're going to do the measurement of our state with our energy detector. In the standard model, O is a very simple operator. It's just made of two quarks contracted for a polarization vector. So this is in principle our energy correlator, and this is the object that we want to study. Okay. And given this object, what we're asking is what we can extract from it. So in particular, we would like to know the spin.
Sorry, just understand whether what is this epsilon? How it is this operator?
This epsilon, I define it
No,
before.
the other one, the last one in the old.
The last one is just polarization vector because I'm gonna.
Polarization vector. So
Yeah, because our operator W will be polarized.
Yeah.
So I have to contract it with some polarization vector that will depend mostly on the, well, actually only from the production, and it's actually what we want like to investigate. Okay. But aside from polarization, this is really a simple expression and just saying I create a state and I measure energy of the states in some given direction. Okay. So the question that we can ask are, first of all, the different entries of the density matrix. So we have W and W star because it's a cross section, and we can ask it's a 3x3 density matrix in DC space, and we can ask how they look like the different entries starting from the energy distribution, and we can ask even other question that actually I put a star because they are not phenomenologically viable, but it just to illustrate here, as for instance, our state will have a mass. So we can try to reconstruct the mass of this object. And in particular, our state will evolve according to QCD. So we can also ask some property about QCD. So also, for instance, spin of QCD or the phase transition in QCD as you move to one angle, similar to what they presented at the beginning. And okay, at practical level, this may look a bit abstract, but actually it's quite obvious what to do. In QCD, we have asymptotic states, say for instance pions. So what we do actually is just insert a complete set of states or asymptotic states in this dashed line that I'm finally defining, and then just compute the action of this energy detector on the states. The action is extremely trivial in this case. is an energy detector. So what it's doing is just counting the number of small x in the state, capital X, of particle going in a given direction. So every time it counts a particle, it just measures the energy. So this is actually straightforward, and the energy correlator that was before can actually just be rewritten at the amplitude level as the amplitude for the production of a given final state X, just weighted by the energy. In fact, they're usually called weighted cross-section. And this is just a normalization factor that will be completely irrelevant to every normalized one when we integrate over the angle.
So, Lorenzo, so the
Yeah.
on the previous slide you had this correlation function,
Yeah.
this endpoint function of these epsilons, right?
Yeah.
So here you're setting n specifically equal to the number of pixels in your detector, basically.
Here I'm just saying I have one detector. So I'm just
one.
detector.
But you sum over x, which are the pixels in your detector.
X are the final state. So
Different final states.
the final state in X. So X is a generic multi-particle final state. So capital X is the final state. Small x is just the number of particles in that state.
Okay.
So I'm doing something extremely trivial. I'm just counting the number of particles in a direction and summing over all possible states, because a priori we don't know what they are.
And I suppose the E with no index is the total energy.
Is the total energy that I'm just taking as normalization. Yes. And okay, and just saying that, but at the end, the point that I want to make, at least for this part of the talk, is that these objects are perturbative. So this means that this exotic object, I mean, not exotic, but anyway, quite complicated, can actually be computed just at perturbative level. So we know that our WZ, they're going to negate just the QQ per pair. So actually, we just have two possible states, a leading order, producing this energy. So everything is extremely simple and can be just computed with pen and paper. So that's the whole idea, is that since it's perturbative, I just compute things here, but I measure them at a wrong level, and I'm going to get something which is close. And we can quantify how close it is. Okay, so this is in fact just basic kinematics. I don't want to go through because it's really trivial, but in principle, we can go in the rest frame of our vector, and in the rest frame, we know that the angular distribution for the QQ bar pair are extremely easy, and they're fixed just by rotational invariance and by the beta and the matrices if you want. So we know that producing for a plus or minus transverse polarized vector boson, this is going to be the angular distribution. So 1 plus or minus cos theta star. Cos theta star is just the angle between the helicity plus quark and my spin vector. Or I can have a sin theta star just for the longitudinal polarization. So everything is extremely easy. I can just take these two formulas, boost them in a new frame, boost also the measure, and consistently all the rest of the phase space integral. And what we're going to get is just some simple expression. That is the end, basically, of this calculation. And just to emphasize that this contains most of the information we want to ask about. For instance, we know that plus, minus, and zero helicity, they have a very different distribution with the angle. This Z is actually the angle, just redefined in this way, which is quite convenient, as I will show in the next plot. And we can also see that plus and minus, they have a different distribution with the azimuth that I'm not drawing here. It's 2D, but it's just the usual azimuth, usually the usual azimuth with respect to the spin axis. Okay. So from this is the calculation that actually you can just go and compare this to what you get with the full simulation and eventually data. And the easiest thing that you can imagine is just to put a single detector in your final state. So just to tell you what I'm simulating here is just plus and minus into WW with one electron in W. So this means that we can just focus on the first guy, which is actually really a monoenergetic beam of W's. So it just takes to have a monoenergetic beam of W's. So include when we have one energy detector, this detector can hit at first order only either the quark or the anti-quark. So studying this angular distribution, we can study whether the original W was longitudinal transverse polarized. And this is basically what we get. The solid line is the calculation that I showed in the first slide. So really the simple level calculation is that the dashed line is what you are going to get at the level. So after all the simulation, after including the effect of the hadronization. And you can see that they are pretty close, given the simplicity of the calculation. And you can use it to do some phenomenology. I will not go through the details, but in principle, what you can see is that the two shapes are slightly different. One has a broader peak and pointing towards smaller angle. This Z is again just an angular variable, so just the distance between the detector and the W momentum axis. and here also putting angles. And yeah, that's basically it.
Sorry,
Yeah.
just a very simple question,
Yeah.
but the reason why the calculation is perturbative because W is very energetic, so you have to.
No, even the reason why it's perturbative is that you're just counting energy. So if you're gonna, I mean, if the quark is gonna say emit just some photon, some question gluon, at the end you're just measuring energy on a detector. So you're sort of coarse graining on all the detail that happen in the hadronization process or in the showering process.
I think Mastin was saying that this is perturbed because the W has 80 GeV mass, 90
Oh yes,
mass.
that's exactly right. Yeah, absolutely. And in fact, the more energetic you are, the more your center of mass is energetic, the better it is. The boost is just a boost factor, so that's why I got confused there. And yeah, absolutely. In fact, then you can try to do something more. You can ask for 2-point energy correlator. Here you have QQ bar, so you don't have many options. Either you hit the core or you hit the anti-core. I mean, you have to hit both of them with the two detector. And what you see is basically that there is a huge peak, which is corresponding to an angular distance. So here, corresponding to the mass of your object. So this parameter Z star, which is just is boosted, so it's just the boost factor. And this is just coming from kinematic. For was trying to do some collider with the usual Jacobian peak that actually is used to measure the mass of the W boson in a different process. And you can see that as you start going to smaller and smaller angle, you start scanning all the different scale in your theories. So for instance, you can see this just at a level. We didn't put the analytic calculation. Would be very simple, but you will not have seen this part here. But you can see that when you go to small angle, what you get, you really get a power law, which is what is predicted by perturbation QCD. Till again, you get some effect of confinement. So when you go to small angle, you start hitting thresholds. So in particular, the threshold of lambda QCD over the energy, and you start having a plateau. And then finally, when you go to smaller angle, you see again free streaming pions, free streaming hadrons, and eventually you just get zero. Okay.
Sorry, that curve is, how did you get that curve?
No, this we just got it from simulation. If you try to do it from theory, you can get it. You're not gonna get this part here because this is really generalization, but you're gonna get a singularity. So this actually here you will just get a straight line. This singularity is because you have a singularity in the Jacobian that will be corrected either by higher order effects, which here are completely perturbative, and by the finite width of the W. So you can do it with. I didn't report it here, but at the end, this effect here, I also want to point out that here everything is perturbative. The only expansion parameter that you have here is really MW over E square, lambda over MW. So this is your perturbative parameter, and it's small enough that you have no problem.
But the different parton shower algorithms will give different peaks, right? In that
I mean,
non-perturbative.
Yeah, the peak.
No, the non-perturbative part.
The perturbative is completely, that is really, I mean, that you're going to compute in perturbation theory or in the normalization algorithm.
Yeah.
So actually, in my opinion, all what we're doing is useful only for high energy, so we don't want to deal with that normalization. But in principle, you can do it, but then you have to pay the price that you cannot compute it, so you need a normalization model or algorithm. Okay. And yeah, let me tell you just the final application, then move on. We've seen plus and minus helicity, we've seen the different scales in our jet. The last part that we've not seen are interferences. So in particular, our W, they are gonna at level of the cross section, if they have different helicity, they can interfere. Plus or minus W versus plus or zero W. And you can do the same exercise, it's really a simple exercise. And to study how when you move the energy correlator around the spin axis, so just within the azimuth, you're going to see the different interference pattern. So to do this exercise, I mean, actually, we were interested in new physics. What we did is just to include in our standard model some new physics effect that always produce two W's with the same polarization. Instead, the standard model mostly produces same list W. So standard model MSM in this simple model here, which is just obtained integrating out the Debye graviton, if you care, will never interfere. I mean, mostly they will mostly not interfere up to mass correction. So the interference, to resurrect it, you have to study some more differential distribution, as for instance, the azimuthal dependence of the two energy detector, or even one energy detector is enough. And what you get is basically that you can really see the interference pattern of the BSM versus the standard model, and the interference pattern of BSM are way more pronounced for this specific model as we were looking for. So, I mean, I conclude here this part of the talk, and just to give a summary, what I wanted to point out is just that this object, we can look quite difficult again, and mostly controlled by leading order dynamics, unless you really don't go in some corner of the free space, like for instance, very small angles. And from the leading order dynamics, you can get most of the property of this object, and you can get most of the phenomenology. And we use it to propose some phenomenology that I'm gonna skip, but feel free to ask me later. So now I'm gonna go to the second part of the talk, where actually I will not talk anymore about phenomenology because it's still a work in progress and we are not still there. But I will mostly talk about the theory challenges that we're facing for this specific scenario that we have in mind. Okay. No more question, right? On this part, so I can go ahead. Okay, I already made the disclaimer. So let me start again by BSM. So new physics BSM, if light has to be with coupled to a standard model. This we know, otherwise we would have seen it in Collider. So it can be either coupled through a mediator or directly. Actually, for this talk, we don't care, but this can be the case. Of course, BSM itself can be strongly coupled, with no reason to say that this is not the case, right? And if this is the case, as I said before, we might produce events with very high multiplicity order particles. And also QCD jet. This is a scenario that actually is very well studied. And for instance, in some case, for some BSM, it's usually called unparticle physics. Now, in principle, this new physics is dark. So if this is the case, what you can study is just how this physics recoil. We say, I guess, standard model, or you can just start the visible part. But when the theory has a gap, the dark state in principle can become visible. And so they can turn again to a sort of standard model jets. So the gap is basically playing the role of really a dark perimeter in some sense. So if this is the case, what we can do is to really look for the correlation of BSM inside the standard model. This scenario is usually called in Hidden Valley, and this is also quite studied in the literature, but it is what we have in mind. And yes, how do we deal with this scenario? And what we have in mind in particular is where we produce this new physics at very high scale, say collider energy, so say for instance TB. But at the end of the day, this new physics will turn to the standard model at very low scale, say GV for instance. So the whole evolution from the OV to the R of the new physics will be mostly controlled by the strong coupling, by the strongly coupled new physics itself. So this is the scenario we have in mind. Now, if BSM is similar to QCD, we know how to study it. We know to study QCD collider. We can just go to our simulation, change a bit the parameter, and try to model this new physics. And in fact, I mean, there are even already that PTR code available. Now, if the new physics instead is a sort of CFT, so for a large range, say from UV to approximately AR, behaves like a conformal field theory, energy correlator may be the only way to go. And actually, this already was hinted by Hoffman and Maldacena in the conformal collider paper. Is to motivate why to study this kind of observable. So this is the scenario that we have in mind, okay? And as I said, we are not yet a phenomenology, and the reason is that we are asking the various theory question that comes with this scenario. And there are three major theory challenges, in my opinion. The first one is how do we deal with a confinement CFT? As I said, we really need confinement. We really need the CFT at some point goes back to standard model, and otherwise we cannot see this sector. So are we sensitive to the gap or not? How do we perform any calculation in this theory? As I told you, in the CFT, we have some handle. We know to compute at least in some regime, but in principle, when we have confinement, it's not guaranteed that we're going to get the same answer. The second point is how do we start the CFT data? So we see energy pattern, but what do we look for in the energy pattern? CFT usually is described in terms of P coefficients and scaling dimension. So at least minimally, we would like to be able to see this effect, or at least to see if there are not this effect there. And the third point, which is that how do we classify all these different CFT? So is what I'm saying completely model dependent? So any CFT is going to behave completely differently, or there is a systematic way to classify this possible infinity scenario so that we can go to data and look for them. For people used to collider, this is just saying that whether or not we need really simplified models, or if we have a really specific principle to arrange our classification of CFT, let's for instance, FTP field theories. So these are the three theory questions that we're trying to address. I will try to just talk, I will just to give a motivation of the first one and why you can forget about the gap, and then we'll tell you something about the second. Okay, does it make sense? Okay. So from now on, of course, I'm not going to say anything anymore about phenomenology, but we're just going to say you something about the model. The two model is very standard. We want to model a CFT, and as I said, with some angle on this model when we have holography. So where at least where we can compute something in perturbation theory. So what we remind is just to use a simple version, simple truncated ADS5. So just ADS where we include an IR brane at some point. This IR brane has one role and is the role of the gap. So is the role of making our theory confined at some point. This scenario is called a scenario for which used to phenomenology, but the only important part is you have this metric, and at some point you truncate the bulk. So you start from from your boundary, and then you put an horizon. At some point you reach this WR before the horizon at the infinite distance. And the state that we want to study is this state. So it's just a boundary operator acting on the vacuum in moment of space up to a normalization. We doing a Fourier transform, so in principle should be useful to normalize this state, and then mirroring it with a finite width Gaussian, and then taking it to 0. I didn't even put it because practically we don't need it, but just let me say it. And as I said, when W goes to infinity, this is really the standard scalar in ADS. So it really a CFT with just one, with this operator being, this operator being a primary operator. When the brane is there, actually it's theory confined. Now, in general, our state psi is a really complicated state. It's a multi-particle strongly coupled state. Sometimes it's called unparticle, and it's a nightmare how to study. And our goal is really to look at energy correlation of these states. Okay. Let me mention two things. One is that there is already actually some at 10, but I'm not going to say much about it. And the second one is that actually it's almost a phenomenological model for what we want to do. That to get to phenomenology, you just need to couple the standard model, which is quite standard in phenomenology, is done just about a new brane here. We don't need it, but just let me mention it is really close to a phenomenological model. Now, what is the problem? And the problem is the following: is that with an IR brane, we introduce a gap. So our CFT, that I call CFT tilde because it's not exactly a CFT, is actually really a regular quantum field theory. It has asymptotic states and it has an S matrix. So in principle, we can describe as before, just in terms of amplitudes. In particular, our field can be decomposed by the separation of variable in what are called PK mode, that up to some profile just tell us that our theory here is made of simple particle with all possible with masses, and this is how the masses range. So this theory is a discrete spectrum of masses that are separated by that are discrete, and the separation is controlled by the position of the IR brane. So 1 over WR. This is very standard, but I just wanted to repeat it to be consistent. In this theory, in principle, as I said, we can attempt to compute amplitudes and cross section. So in principle, we can compute the transition amplitude from our initial state psi, which is not an initial, which is some state, up to some asymptotic state, which is now made of different PK mode. So in principle, it's a multi-particle state. Okay. Now, if we try to do that, unfortunately, we immediately find a problem. And the problem is that at 3 level, the theory is pretty boring, and it's just made of these 3 hadrons. Every KK mode is actually an hadrons just flowing around. And so the theory has nothing to say. But as soon as we put interaction, and we must put interaction for consistency, is the KK mode acquire a width. And just to show you what happens is if the width is linear with the mass of the KK mode, when I go to highest excitation number, the width becomes large compared to the gap. This means that this KK language is completely cannot be used. So we can use the KK language as far as we just excite energy, which are still in the discrete part of the spectrum, where we can still use the narrow weight approximation, and at least we have a numerical way to simulate this cascade. So it is that you produce a state here, this state is going to decay eventually to the left KK mode, which is the only stable one, and you can simulate this numerically. And this is done in some phenomenological study. There are way more that I'm not even quoting here. But when we go to high excitation number, this is not consistent anymore. And in principle, these states are not in any sense an asymptotic state, not even approximately asymptotic states. And so we have to find a new way to deal with this theory in this regime. And this is the regime that we remind. Okay. Now, in QCD, let me go back to QCD. Usually this we face a similar problem. We want to use perturbation theory, but then when we go to experiment, what we have is really just a bunch of hadrons where we cannot use perturbation theory. So, but we know that implicitly at the end, this is not a problem. As I said before, for instance, if we just want to compute the hadronic decay width of our W and Z, as we are used to do, we never talk about hadrons, but we just compute in terms of quark and gluons. Okay? And we also seen that energy correlators are largely insensitive to confinement. In a second, I'm going to give like a stronger argument. And so we know that if we're a large angle, at the end, we can just forget about confinement. So we would like to argue the same in this theory. So the goal is the following, that we would like to have to work in the CFT, where we have some angle, and forgetting about the gap. And we want to give at least a qualitative or more strong argument to say that this can be done. So, for instance, the total production section for any of this state in the CFT, so without the gap, will just be the simple formula. So just the Fourier transform of the two-point function is a Weichmann, so you put the correct plus or minus a epsilon, whatever. Instead, in this theory, it's different because we know that we have a gap. So we just have a bunch of discrete modes with some weight, which can be computed. But we also know that at the end, if we are not extremely precise on the momentum flowing in our state, so if we include, for instance, a weight or we just mirror over the initial state, at the end of the day, the two expressions looks exactly the same. I guess you all agree on that. At the end, when it starts mirroring, the gap in this sum n is controlled by one over WR, which is very small compared to the momentum we're thinking about. So at the end, when you convolute this function, I guess any smearing function, which has a quite small smearing parameter, at the end, the two expressions on the right and on the left, they will look exactly the same.
Does meaning as a meaning in terms of like you're looking at times which are not too long, something like this. I remember this paper by Strumi and Riccardo on the
What you're saying
scalars.
again? No.
I mean,
what I'm saying here is something very easy. It's just that, on the right-hand side, we're really working at the level, so we're not really putting any interaction. But since we're asking about inclusive quantities, we basically get the same answer as the CFT, unless you're not asking
no,
something
I
which is
understand what you're
extremely.
saying. That's one.
Yeah.
Yeah, maybe I can ask you later.
Okay.
But so the smearing should be larger than 1 over W.
Yeah, but which is a very small parameter compared to P.
Compared to T. So
That's
it's
the
large energy
Yeah.
and smeared over 1 over WIR, which is a time. Time to go from one point to the other.
Yeah, exactly. So it's like you're not giving enough time to the KK modes to bounce back, something
Yeah.
like this, right?
Okay, let me also say that this is 3 level, so then it's not the truth. So you're going to put interaction.
Yeah,
and
but thank you.
I mean, in terms of time, you're saying that you cannot resolve this time scale if you want,
Yeah.
because that's what you want to argue. So we would like to argue the same for energy correlator, and it's basically quite hard, so we're going to give just a theory argument. And the theory argument is very simple, try to stay with me, and energy correlator, I mean, first of all, for large angle, in principle, we don't expect anything wrong. We don't have any small scale, we have the angle, which are order 1, and we have 2 parameters. One is the energy, which is large, and one is the separation, so it's the width. Sorry, is the spacing between the decay modes, which is small. So in principle, as for the previous example, for the total cross section, at the end, we don't expect any big difference, right? But so if something goes wrong, most likely it's going to go wrong to small angle. Now, at small angle, we know that this energy detector, I'm going to explain in a second, they satisfy an operator produce expansion. So I know that if I put two detectors together and they start putting them closer and closer, at some point, they will basically look a single detector, just a new different detector, but just a single detector. And physically, I guess this makes quite sense. At the end, we're just bringing 2 energy detectors together, and when the angle is extremely small, I really don't know if I have a single pixel or 2 pixels, which are very small, I mean, very tiny separated. Okay, and this means that in principle, our operator, they satisfy some OP, and this OP is given in terms of no-local operator that I don't want to define, not to bother you, but is completely fixed by the selection rule of the CFT, so in particular by the twist of this operator, and J, which is actually how this operator transforms into the boost, which is usually called spin. Plus, and this is plus other terms which are less singular in theta. So this is really the leading behavior. And the fact that you have J equal to is actually fixed by conformal symmetry. Okay. Now let me give you also another physical intuition and what this is what this doing in what this does in QCD. So in particular QCD, what we're saying is just that if we have a quark, we measure its energy, but we also measure the energy really nearby, where most likely we're going to see a gluon or some product or some splitting on this quark. At the end, when we go to extremely small angle, we can just replace this two detector by a single detector. And given these two, we know what we're going to measure in the single detector. And this single detector, what it's going to do actually is just to measure the energy of this quark, for instance, in this direction, weighted by some power. J equal 3, so this be energy square. I guess this is extremely obvious. We have energy here, energy here. When we go to very small angle, what we're doing is just measuring the energy square of this object, times some weight that I didn't compute here, but I just wanted to illustrate what this operator is doing. Now, if you want to write this operator in terms of field, it's actually quite complicated. It's not local, and it's not even the integral of a local operator, at least for odd j. For even j, you can write down as the integral of a local operator, similar to what I did with the stress tensor at the beginning. But in principle, no, but we don't need it for now. Okay. And so this is the idea.
So
Yeah.
in this case, like 1 over theta square is obvious.
So 1 over theta square. I mean, this depends on twist. In QCD, when
It is 2, right?
twist 2. Yeah, so it's 1 over theta square. That is what you expect from the splitting amplitude. Just because the propagator over a quark before splitting just goes like 1 over q squared, and you can map this q squarely with the angle in the splitting. I don't know if it's been clear, but you know, it's really just simple Feynman diagrams.
Okay.
Okay.
But it comes from symmetries, right?
Comes from symmetry, yes. So this is the lowest twist in QCD. In general, in our theory, we don't know. We can have any kind of twist with the stress tensor. So you know, there is at least some operator that we know is there, and plus we have our scalar.
No, just to understand this comment of the less one is 1 over theta.
Yeah, I mean, you can add other term. You see theta minus 4 that go with our higher twist, and they will have more power in theta. Since we just want to see the leading small angle behavior, this is just the first
1 over
theta.
theta square.
Okay. And okay. So for my insisted small angle behavior, yeah, the small angle behavior is controlled by FOP. You can classify it and go through the theory. Just let me tell you what are the quantum numbers of this operator, just to check that this equation is correct. So is the J, which is actually the boost. So the angle under this operation shrink or becomes larger depending on how you define it. And for some, I mean, for a reason, post-historical J and tau actually are related to the real boost of the operator between this formula. But basically, just classifying boost and dilatation, and you know the right-hand side, you can guess the left-hand side. So I'm just saying that this is completely fixed by symmetries. Okay. Now, with their brain, at least in the simple model, WR spontaneously display conformal invariance. And so this means that we have a spurion, so a field that is going to realize conformal symmetry if we associate to it the correct transformation properties. This basically means the following, is that we can basically start adding some over power 1 over WR, associating just what we expect from dimensional analysis. So it's not going to change under dilatation, but under boost, but it's just going to bring some power dilatation just because it's a scale. So what we can do is just to add another term and then compare the two terms. And this is going to tell us basically that if E is the hard scale of our process, so square the mass of the W in the first case, just comparing the first guy and the second guy, we can see that for angle larger, than 1 over WRE, so of the ratio of the masses of the two scale, organization is not important or is important. So at least we have an idea, which is what is basically given by dimensional analysis. Okay. So this is another one just to say that. So we can basically just use.
Can you upgrade this argument to a systematic way to do perturbative calculation?
I mean,
1 over WE, like start from conformal and then the conformal behavior.
I mean, I guess so. Also, something I said to say is that here, in this model, this effect is really spontaneously breaking, but then you will never have it, and because you have to stabilize the airbrains, is what you're asking. So you have to add extra correction that you can systematically, if they are small, basically.
And then the leading effect here cancels, and then you have to go to subleading 1 over W square, maybe.
No, I'm saying that this is the leading effect, and is here as far as you have this operator in your spectrum. You can have other operator, but maybe I'm missing your question, but yeah, that's the answer. So you can, if you don't have this operator, it's going to be another effect.
Okay.
Now let's assume we have it, and actually in our theory we have it. And so this is the leading effect. So, okay, and actually the argument also works in QCD. In QCD, I will not be able to explain what happens because I mean, there in particular, the confinement is not spontaneous. So we cannot say that lambda QCD is a spurion, but just by image analysis and fixed approximation, we can think about it and it kind of works. So in particular, these guys here, they are basically showing this 2-point energy correlator as a function of the angle. This is the angle just normalized by the energy, if you want. XL is really the angle. And what perturbative QCD predict really a scaling law, and you can see that you really get a scaling law. And when you go to small angle or to large angle, where you start having other kind of effects, so threshold effects, you see that the scaling law is broken. And again, when this kicks in is really what is controlled by it's okay.
So also in your case, WIR was fixed, or you imagine some scalar stabilizing it.
I mean, correspondence breaking, you cannot have any scalar stabilizing it. When you're scalar, then you do deformation of the CFT. So you have to work in perturbation theory in the inclusion of this scalar.
WIR for you is
It's just a free parameter.
just a free parameter.
Yeah, in
It's
this model,
to truly have a dilator.
it's really a free parameter, it's really a flat direction. So this is the starting point, and then one will try to add all the correction. But yeah, absolutely, that's a good point. Okay, let me go on. Try to close. Okay, so what I argue so far is that if we believe the argument, energy pattern, we can just work in the unbroken CFT. So now what I'm gonna ask in the rest of the slides, how this energy pattern they look like in this model and how do they behave. Let me say also this calculation was already done long ago, actually by Hoffman and Baldaceno. They use conformal invariants in got to a specific frame, and they use for some extra solution. The way I'm going to present it is slightly different. We're just basically using weighted diagrams to show that. In particular, we know that in flat space, to compute this energy detector, no one asks an equation. It's quite obvious. I have our W equals to quark and gluon. Every time I see a quark or a gluon, I just basically measure the energy in a direction. So we would like to have a similar approach also here. And the idea is that you can do it. It's a quite boring calculation, so I'm not going to go to the detail, but I just want to highlight some physics. In particular, what we have is just that now, for instance, the single expectation is given by this weighted diagram, where I have some operator, some other operator, which is the same actually, in moment of space, and just some energy detector. The energy detector is put on the boundary, so it's going to propagate to the bulk. So this simple weighted diagram, that you can look even here, if you're more familiar with the notation, it's just going to give the result, simply. Okay, now just let me highlight how the physics of this calculation, because I find it quite nice. First of all, we know that if something has to happen, I mean, if this conformative theory is doing anything, it has to do it for large W. So what I'm going to do is just to expand the wave function, this propagator, for large QW, where Q is this momentum and W is the direction of the fifth dimension, just to know what happened when we are very close to the horizon. And what we can see is that basically this is just expression, it's just a simple cosine times the initial wave function. Don't worry about any prefactor. I would just want to say that this object, when I go very deep into the bulk, and when I go very deep into the bulk, it's just going to oscillate, just like a cosine. It's just a plane wave. Okay. So you can see that when you go to large Y and large W, so Y is the position of this interaction. This oscillation is very, very fast, unless your position is not localized in some function of W and the momentum. Okay? You can do it formally, adding a smearing and then sending the spinning to 0, and just trying to say that this is the leading trajectory in the bulk integral. Now, it's interesting to see how this interaction very deep into the bulk look like from the boundary, because our detector is on the boundary. Okay? So if you write down the distance between the two up to a redshift factor, you see that you have this expression. So you have a term which is quadratic in the T minus R square, where this is the position of the detector, times term which is linear, so linear in W and linear in X. Now, you know that when R is very, very large, the first term will dominate. Unless XT, is the position of the detector. What I'm trying to say is that just that when you go to very large R, in order for this distance between the interaction and the detector to be small, you favor position, you're dominated by T almost equal R. These are the trajectory that you expect from a serious particle. And in fact, we know the trigonometric function is fixed by conformal invariance, and we know that in a conformal theory, signal asymptotically propagate at the speed of light. We just say that this simple calculation shows this fact. So what we actually, from the 4D perspective, we are trying to model is a particle that starts evolving. If you think in length, it starts to decay, and produce way more KT modes till you reach massless KT modes at the end that they propagate at the speed of light. Okay, now you can do the calculation properly, and you can also see that actually the limit up to infinity really localize the interaction. So where you perform your measurement at the bound, at the horizon. Really at W infinity. So this is because this is an error measurement to really wait for your particle to reach the ER as much as you can, and then you do measurement.
But then that would be sensitive to the wall. You truncate your space, then the signal will lie on the wall. So that would be.
Yeah, but it does mean that it's different. So I mean, the measurement is done in the ER. That's what he's saying. He's not saying that the measurement with a wall is different from what you expect without the wall. But that's a good point. So he's saying that technically you have to wait for this guy to decay and then do the measurement. That's what you expect from physics, right? You just have to wait late time because the detector is very far. Okay. And now you can do the calculation properly, and what you're going to get is a Feynman rule, which is extremely similar to what we had in flat space. I don't want to go into detail of this unitarity relation, but in principle, you can just decompose this propagator in terms of 4D KT modes, even in the CFT, and so you can really board the unitarity relation from flat space. But what you get is that basically what the detector is doing is just really measuring the energy of the particle, but the detector is measuring with this factor, which is not just the energy going in a direction, but is an energy distribution which is spread around. So for instance, if you are in the center of mass, this is completely isotropic, and you have just a complete isotropic factor that covers all the celestial sphere. Now, as I said, this triple function principle is fixed by conformal invariance, so this calculation is, you can just do it with conformal invariance. But the nice part is that once you have these diagrammatic rules, you can just go on and compute the triple function. The first detector is gonna measure the energy in a direction. This N1, again, it's a lightly, it wrote it, but it didn't say it's a lightly vector with 1 and N1, and the same for N2. Now, to detector, what you're going to do is just to measure the energy in these two directions. So instead of get a 2 delta function, as we do in when we have for just in perturbation theory for usual for the particle, you're just going to get some factor this form. Okay.
So you're saying the rules are like the ones you showed in standard particle physics, but like now.
Yeah, just with a.
So you can forget about the integrals over the fifth dimension and.
To get this, you are doing the integral.
Yeah, so you already did it basically.
Yeah, you already did it. Yeah, I mean, if you want this trick, just to have some physical intuition. At the end, this is a particle propagated in the bulk, and I'm asking how this particle look like. So the energy is not just localized in a direction, but is spread around with this function. Now you can also see that
there is some saddle point that went there, or is it completely systematic? Is it exact, or there is some saddle point?
No, this is exact.
It's exact.
Yeah. I mean, actually, it's the same result that of my design they got with their shock wave, and
Yeah, but it's.
I mean, it's exactly 1/n. Yeah.
Really,
just the diagram. No, that's really the exact diagram. Okay. And yeah, so what is describing is an energy distribution which is dense and isotropic, is for instance Q equals 0. And this is consistent with the very rapid fragmentation that we expect as from coupling that was argued in different way already long ago. Let me also say that in the case when Q squared becomes 0, so this particle becomes massless, you exactly get the other result of the flat space, just because the particle cannot decay anymore. It's not obvious from here,
but here is it entering the shock gravity?
Gravity you're just using as a sort of detector.
No, but I mind this paper by Sasha where they show this shock, super convergence, blah blah. They argued if you add derivative couplings,
yeah,
then this result might change.
Exactly. I mean, this is a leading order in this.
So you switch. So here you like is your form. I understand is that your prescription breaking down, or is just that
the prescription breaks down at very small angle. You don't see it at 3 level, but it breaks down. I mean, that's more detailed. I mean, you don't see the calculation, but you know that it breaks down.
Okay.
So if you want when the angle is exactly 0, this is not defined. So in some step of the calculation, this part which is not defined. Okay, but let me try to summarize. So in principle, you can compute a more complicated diagram. And what you see is that the energy distribution leading order is very boring actually. So it's just given by all this factor. So if you go in the next frame, this completely isotropic distribution. It's isotropic and dense, so you can put the detector in any position and you're always going to basically measure the same. Now, from one side, this is good because it is quite easy, but from the other side, it's pretty boring, as I said. So in particular, we don't have any information about the theory, aside from saying that the theory is large n, that is our assumption. Next to order dynamics is more interesting, but it's more theory dependent, so we don't know yet how in general will look like, and there are already different results n equal 4. Let me also mention, I mean, not important, but that this result here is actually not only a large n, but for instance, as we found with Gabriel, I mean, we found even before, the same factorization work also when you have large charge. There is quite more intuitive because you just have a state which is very heavy in some sense, and in fact the same is expected for every state in general. So for the interesting dynamics, you really need to go on next leading order and look for something more. Now we have something more that we can say about this theory in general. Small angle are dominated by operator with the lowest twist. So you know that if you go to small angle, what you're going to see is just the lowest twist spectrum of the theory. So that's already some more information that we can use to characterize what we want to see. And another point that I was very fast is that these diagrammatic rules actually they are quite useful for practical calculation. So in principle, you can write down a very complicated diagram, which is also complicated. I mean, this sort of diagram. And now, as before, you were basically computing the energy in a given direction. Now you can just weight this line by these two factors. And at least you have a closed form that you can put on a computer and just compute the shape of this correlation. And yeah, so I guess I'm gonna conclude. Before terminology, I said that we have many theory challenge. The first one is how do we do this calculation? Can we use the CFT, or we have really to use our broken CFT tilde? And this, at least I gave you the OP argument saying that for large angle and as large as we said before, so just what is basically image dimension analysis, we most likely can just use the large angle result taken from the CFT. So at least we know how to do the calculation. We also know that B, the leading order dynamics, is universal and factorized. So the formula that I gave before, and that NLO dynamics that is more theory dependent is more interesting. These diagrammatic rules can help the calculation, but we also have additional information about the spectrum from OP scaling law. There is a third point which you see, which I didn't go through, and in principle, as I said, we would like to have a systematic way to characterize all possible CFT beyond the standard model in a way to efficiently check with data, but we don't know yet because energy correlator are obtained by really not real manipulation of Lorenzo correlator. So aside from the diagrammatic rules, which looks quite simple in general, to do this calculation, really you have to do not real manipulation to a Lorenzo correlator. So we don't know if we can systematically use at least effective field theory in ADS to systematically parameterize the space of CFT and to really have correction controlled by an effective field theory, at least in ADS. So this would be, if you want, one of the goal. And the main goal is clearly that energy correlator, as I said, give access to a new exciting dynamics and I guess also new exciting theory. So we would like to apply it to real world phenomenology. And I close here. Thank you.
When you computed corrections that were subleading in 1 over W IR, you said this is for the radion where you have a flat direction.
Yes, from the radion.
Now, don't you expect then you have to break this flat direction, give a mass to the radion pinpoint?
Yeah, you have to do it.
So
there will be correction.
Yeah, there will be correction, but these corrections could be bigger than 1 over WIR. Right? I mean, for instance, the mass that you give to this.
I mean, it depends how you break this correction. To say,
in particular, in a model that vaguely resembles our own world, is there a hierarchy of correction in which the scale set by 1 over WIR is bigger than the scale of explicit breaking of the.
I mean, I don't know. Honestly, let me say that in a model that resembles our world, I imagine the correction can be in principle bigger, and so now you might ask why QFT works. And my answer is that I don't know why QFT works, but it works. Now, but you also read that we can have a model where this correction are controlled and are small. So that's what we remind. So, but it's a very good point. So if you ask me why it works, I don't know, honestly. But phenomenologically it works.
Okay.
I mean, there was simulation, so we can check. And, yeah.
So I think we kind of asked if if we're going to the 1/n reaction, which are hard, I mean, what about the soft breaking of conformal invariance?
No, I was talking about that, not one.
Yeah.
Right.
Yeah,
I mean,
I was
you
asking
say
like,
systematic-
what would it be the?
Diagram.
Yeah, let's say one thing, what, even in your model that speaks WIR by a miracle.
I mean, well, I didn't pretend we're trying to do this calculation, it's not so easy. So that's we do systematically. I can tell you the linear the result. The linear result is that when you put WIR, you just have free streaming hadrons. So if you go by brute force and do the calculation, what you find is what you find in plot space. You measure the energy on hadrons going in some direction. This doesn't mean that it's the correct answer. Because
But
when
you probably don't expect to be able to go.
yeah, but this will be given by interaction. Because you must have interaction. So what we expect, and we're still not yet there, but we can do something is that when you put interaction, what you're gonna get is some shape which is similar to what you have in QCD for large angle, but when we go to small angle, it's not similar. Whatever interaction you put a large angle, you should get the same shape. If you want an example, is the 2-point function that I showed at the beginning, not between energy correlator, but just the total decay width. With the brain, it's just a discrete spectrum. When you put interaction, no matter which interaction you put, it always resembles the one in the
I think I
system.
was asking, really in the systematic regime, well, what you call the transition in QCD, there you should have perturbative access using WIR spironic.
Yeah, but if you go straight and do the calculation, you don't see the perturbation theory.
You
So
don't
you
see
see
it,
that.
you're saying.
Yeah.
But from your OP argument, you kind of add.
For the OP, working the interacting theory.
Yeah.
So what
okay,
we do matter is that you put the interaction, you do the work calculation, at the end you're gonna get
okay.
something that resembles CFD. So I mean, we're trying to do it and with some preliminary result and then show because it's still preliminary. But just to say that it's not so trivial, you cannot just go and put the brain, because if you put the brain, you just get all tower decay modes and decay one to each other. And so in principle, it's not perturbative. The final result is to be perturbative
Okay.
using CFD rules. So yeah, it's not trivial. But it's what we're trying to do with some idea, and we expect really to see a sort of transition.
There are no more questions. Maybe we can thank Lorenzo again.